by Tau Beta Pi, where today we talk about equilibrium and all the fun chemical stuff that comes with it, including Q, K, these little double arrow things, an ICE or ice table, and La Chateaus something French's principle. All coming up and more right here on the drawing board. So what is equilibrium? That's a good place to start when talking about equilibrium, right? So equilibrium has to do with two reactions. So over here we have CC plus D of D forming A of A plus B of B. So that would be the first reaction going forward. And a second reaction, or what we know as the reverse reaction, so BBAA forming DD and CC. So while these reactions are one and the same, they're also both different. What makes equilibrium unique is we can look at how much of one side we have versus the other, either the reactants or the side on the left, or the products, the side on the right, based on something called the equilibrium constant. That is written as K. Sometimes you'll see it as KEQ or KC or KP. We'll cover what all those are, but all of them are equilibrium constants, and they are equal to the concentration of the products, in our cases A and B, raised to their stoichiometric coefficients over the concentration of the reactants raised to their stoichiometric coefficients. So why do we use this little double arrow symbol to represent equilibrium? Well, since we have two reactions here, one going forward and one going backward, we can use it to easily show that instead of just a single arrow going like this, which would represent 1, this is how we can represent 2. So we talked earlier about all those different kinds of K that you'll see, and they all form around KEQ, which is your equilibrium K. It's your most generic type. So out here we have KC. This is probably the type of K you will see most often. This stands for K of concentrations. So on the previous example, where we had those concentrations, this was technically a Kc value. Now over here we have Kp. This is K of pressures. Essentially, when we're using a Kp, instead of solving using concentrations, we will solve for Kp using the partial pressures of everything we have in our system. So you'll commonly see Kp used for gas phase reaction. Finally, we have Q. Q down here is K when we are not at equilibrium. It's also known as the reaction quotient. We'll talk more about that later on in this video. So what can we do with these values of K? So K will tell us a lot about the reaction itself and what's going on. So if our value of K is greater than 1, this means that we have more of our product than we do of our reactant. If we look back at our K equation, which is K equal, for this reaction at least, it would be Cc times D, concentration of D, add my concentration bars in here, over little a, concentration of A, little b, concentration of B. So if we look at that reaction, if K is greater than 1, that means our numerator is larger than our denominator, meaning that we have more of the product than we do of the reactant. On the other hand, when K is less than 1, we have more of the reactant than we do of the product. Now, we'll often call this pushing the reactant to the right or to the left, meaning that the reaction is either pushed towards the right side of our equation, being the products, or the left side being the react. So when we talk about equilibrium, there's one very important piece that you'll need to know for solving any problems involving equilibrium, and that is the ICE table, or the ICE table. So what is an ICE table? It stands for initial, change, and equilibrium. So this is how we're going to solve for our equilibrium amounts of everything, or all of our species that we have here. So if we begin on our initial part over here, you'll notice that for this problem, which is 2H2 plus O2 forms 2H2O, very simple reaction, we already know all our initial concentrations. We know we start with 5 moles per liter of hydrogen, 5 moles per liter of oxygen, and none of water. We also know our final equilibrium of hydrogen. So that is 1 mole per liter. So what we can do now is fill in the rest of this table. So since we have all our initials, we'll go to our change. This is how much we expect to either gain or lose in concentration of each species between the initial and the equilibrium. So for hydrogen, since we already have the initial concentration and the equilibrium concentration, we can just fill that in. That would be minus 4 moles per liter. Now we can do the same thing for oxygen, knowing what we know about H2. But the problem is we don't have an equilibrium concentration for oxygen. Well, this is where our chemical equation up here comes back in handy. So if you look at our stoichiometric coefficients, 2, 1, and 2, specifically compare hydrogen and oxygen, we can get an idea of the change we find for oxygen. So we know for every 1 mole of oxygen that is consumed, 2 moles of hydrogen is consumed. So if we know that we are consuming 4 moles per liter of hydrogen, that means we would consume half as much oxygen. In this case, that would be -2 moles per liter generated of oxygen. And then if we subtract those, at equilibrium, we then have 3 moles per liter of oxygen. Now finally is our water. So we start with 0, but for our change, we once again go back to the chemical equation. We know for every 1 oxygen, we make 2 waters. So since we have -2 oxygen, that means 2 oxygen is consumed. We then know that 4, or 2 doubled, moles per liter of water is created. So that means at equilibrium, we start with 0, we add 4, we end with 4 moles per liter of water. So these are our final equilibrium amounts. So we've rewritten the table here, but now what if we want to know our value of K, or our equilibrium constant for this reaction? We write our reaction back out just so we have it, and 2 hydrogen plus an oxygen yields, or might not yield, 2H2O. So now our K value, since we've been working in concentrations this whole time in moles per liter, this will be a KC equals. So first we'll want the concentration of our products on the top. So in this case, that is water. That'll be 4 moles per liter. And we are going to raise that to its stoichiometric coefficient, or 2. Since that's our only product, that'll be the only thing on the top. So we'll go to the denominator now, where we'll start with our hydrogen. So our concentration of hydrogen ends at 1 mole per liter, and that has a stoichiometric coefficient of 2, so we'll square it. And we'll multiply that by oxygen, which is 3 moles per liter. And we would raise that to the first power, but we don't need to write that. And when you do all that math, you end up with 16/3, which comes out to like 5 1/3 or something, but I would just leave that in the form 16/3. And that is as easy as it is to calculate your equilibrium constant. So one other thing we need to talk about with equilibrium is Le Chateaus Principle. So Le Chateau was some French dude. He made a principle about equilibrium, and we all use it to this day, and hence why you all are learning it today. So Le Chateaus Principle essentially tells us that whenever an equilibrium is put stress on it, so for example, we either heat it up, or we increase the pressure, or change the concentrations, essentially if we do anything to an equilibrium, the equilibrium itself will change to re-establish a healthy equilibrium, or an equilibrium at a lower energy level. So this can happen in multiple ways, as we mentioned earlier. The easiest one is temperature. So what will an equilibrium do if we change the temperature? Let's say we take the temperature and we put it way up. Like we increase it by 50 degrees Kelvin. Well, naturally, to reestablish equilibrium, our chemical will want to release all the heat it has. So it will go to the side at the lower energy level. So how will you decide what that is? So let's say we have a reaction, make it A yields B. Now this reaction will have a delta H value given to it. So we'll say delta H equals, we'll just say 100 for now. So if delta H equals 100, that means for every time we turn an A to a B, we gain 100 units. We'll say this in kilojoules per mole. So for every mole of A we turn to B, we gain 100 kilojoules. So this is what we would then call an endothermic reaction, meaning that our products, B, has a higher energy than A, which has a low energy. So back to Le Chateaus principle, if we take T and crank it way up, we're going to want to go to the side with the lower energy level, which would be our reactant side, our A. So that means our K value for this reaction would drop. Another thing we can look at with Le Chateaus principle is pressure. Now generally if we're looking at pressure, this is for a gas phase reaction, as liquids don't really care about pressures, and we generally don't measure liquids and pressures anyway. But we can look at this as if we have a reaction like 2A equilibrium with B. When we raise our pressure, raise it, in order to reestablish equilibrium, the equilibrium is going to want to go to the side with the fewest moles on it. So what do I mean by fewest moles? Well, if we look at the left side here, we have a stoichiometric coefficient of 2, so that means our total moles on the left side here is 2. On this side, we have just one little B, so this means there's 1 mole on this side. So that means for every A we convert to B, we lose 1 mole of molecules. So when the pressure rises, we want to go to the side of the lower. So in this case, we would want to shift our reaction to the right, meaning K would increase. Finally, the last thing we can do is change a concentration. So if we change the concentration of reactant A in reaction A plus B yields, or possibly not, C plus D, and we take A, concentration of A, we crank it way up. So since we've now put in an excess of A on this side to reestablish our equilibrium, we're going to need to push our reaction away from that A, or we need to convert more A into C and D. So when we do this, our reaction is going to be pushed to the right again, means once again our K value will increase. Now, this is very basic Le Chateaus principle. There are a ton of calculations that can be done with this kind of stuff. Feel free to go look up those on your own time, but this is just a quick introduction to the principle and as it pertains to equilibrium. So there's one final thing we need to cover with equilibrium, and that is Q, otherwise known as the reaction quotient. So what is the reaction quotient? In its simplest form, it's pretty much K, except it applies at any time. So K, when you're looking at it, represents just the equilibrium. That's why we give it this EQ on it. Now to get a value of Q, we do not have to be at equilibrium. So what can that help us with? Let's say we had the simple A plus BB yields CC and DD reaction, and all our concentrations were at 1 mole per liter. That means our K would be 1 times 1 over 1 times 1. We'd have a K equilibrium of 1. Now let's say I came in and I added more A to our system. Now the second I do that, because of Le Chateaus principle, we are no longer at equilibrium. The equilibrium has to reestablish. Now if we want to know where that equilibrium is going to reestablish, we can get an idea by using our value of Q. So let's write out Q for this new system. So I still have 1 mole per liter of C. I still have 1 mole per liter of D. I added an extra mole per liter of A, so now I have 2 and still 1 of B. It's going to give me a reaction quotient of 1/2. Now in this case, we know that Q is less than K, meaning that we expect our K to drop in order to reform our equilibrium. Once again, there's a lot of math you can do with this if you want to be more specific. For today, that is a quick explanation of what the reaction quotient is. All right, finally, in summary of this entire video, we learned about equilibrium, which of course is all based around this little set of double arrows, meaning our reaction can proceed forward or backwards depending on its environment. We looked at the 3 different kinds of K, so that is KC, KEQ, and KP. Or of course, KC is concentrations, KP uses partial pressures, and KEQ is just the generic term for an equilibrium constant. We also used ICE tables, or ICE, which are initial change in equilibrium tables. These help us find our equilibrium concentrations for all of our reactants and products in a system. And finally, we learned what Q is, and we learned how to use that along with K to find different properties according to Le Chateaus. That's it for today, and that completes our series on general chemistry. For the Tau Beta Pi Iowa Alpha chapter, this has been the Drawing Board by Tau Beta Pi for general chemistry. Well, thank you all for watching, and we will see you next semester for more engineering videos.